Hello, everybody. Thank you very much for joining us. And this is, I lost track already, but I think it's the 16th NANO Webinar. It's a series of webinar under one of our global projects. Before I introduce our speaker for today, I would like to briefly explain for newcomers what is NANO. NANO is an alumni network for NF, Nippon Foundation, and POVO, the Partnership for Observation of Global Ocean Capacity Development Initiatives. The former and current scholars are joined by our network with the intention of maximize benefits from the training we received, but also to facilitate active contacts among alumni and the instructors, and to promote joint research activities that were built during the training. One of the research initiatives we have is the NanoDope project, which is an acronym for a global study of coastal deoxygenation, ocean acidification, and productivity at selected sites. This project encompasses 37 monitoring stations around 18 countries, all managed by former scholars or members of our network that monitor, as the name says, essential ocean variables with the intention of observe and analyze deoxygenation, ocean acidification, and productivity. One of the objectives of NANO, not only it's the monitoring of these variables in coastal stations of developing countries, but also to promote outreach and capacity development initiatives. And the NANO Webinar Series is one of them. So we invite at least once every 2 months one of our members or other research experts to talk about subjects of interest, not only to NANO members, but to early career researchers everywhere. So today we have the pleasure of receiving Dr. Sudheesh Valliyodan. I hope I pronunciate your name correctly, Sudhi. Sudhi is, or Dr. Valliyodan is a chemical oceanographer specialized in oxygen minimum zones, biogeochemistry in the Eastern Arabian Sea. He has a master's degree in hydrochemistry and a PhD degree in marine sciences, both from the Cochin University of Science and Technology. During his PhD, he focused on the development of seasonal oxygen deficiency over the southeastern Arabian Sea and its impact on potential greenhouse gases. Dr. Valliyodan's research interests, as per his several peer-reviewed international publications, include OMZ biogeochemistry, nutrient cycling, ocean acidification, and their role in the marine ecosystem dynamics. He has worked at the Center for Marine Living Resources in Ecology as a project scientist and is currently a technical officer at the Central University of Kerala. Sudhi is a former NF POGO Center of Excellence in Observational Oceanography scholar, and he also serves as a guest associate editor for the Frontiers in Marine Science journal, particularly in this special issue of recent development in OMZ biogeochemistry, and is an International Indian Ocean Expedition Early Career Scientist Network member, actually from the core committee member, and has been elected to co-represent the early career scientists of the European Geoscience Union Ocean Science Division for 2023. Sudhi, thank you so much for taking time to present us your work. The presentation is entitled Oxygen Deficiency and Biogeochemical Response in the Eastern Arabian Sea. Dr. Valliyodan will present in the next 30 minutes, and then we will be opening for questions. You can either raise your hand and wait to be named to make your question in video, or you can chat in the chat space. Okay, we are, so sorry, just one more notice. We are recording this presentation and uploading later on POGO's YouTube channel. Sudhi, thank you so much.
Thank you, Lika. Good morning, good afternoon, good evening, wherever you are. First of all, I would like to thank NANO and the coordinators Lika and Subrata especially for giving me this opportunity to present my research in this platform. So today I will talk about a little bit about how the oxygen enters the ocean through different processes, and what are the different processes responsible for the formation of oxygen deficiency, and a little bit about where my study region and how the biogeochemical response of my study region, that is the Eastern Arabian Sea, under the oxygen deficient conditions. So we know there is a lot of oxygen in our planet, but very little in the free form. This is the third most abundant element in the universe after hydrogen and helium, and the second most abundant element on Earth, and most abundant in the Earth's crust. So most of the oxygen are bound in rock or soil as oxides or different mineral forms, and much of the oxygen bound in water as H2O, and we know very little oxygen is in the free form. In the ocean, especially, it's only something like a 0.6% of atmospheric inventory is dissolved in the ocean. So, if you look at the sources and sink of oxygen in the ocean, there are mainly 5 processes that controls how the oxygen can come into ocean, how oxygen is removed from the ocean. First one is that the exchange at ocean atmosphere boundary, then the solubility that depends on the temperature and salinity and photosynthesis. Through that process, the oxygen will be produced, and through the respiration, oxygen will consume. And there are other processes, the ocean circulations and the adduction of different water masses also carry some amount of oxygen, and the oxygen varies depends on the oxygen gradients in that water mass. I will explain this process a little bit in detail before I enter to the core of the topic. So in the ocean, if the ocean contains more oxygen, that is more than 100% of oxygen. So we typically this will be called as saturation, the supersaturation of oxygen. And in this case, the ocean start releasing oxygen to the atmosphere. In case the ocean has little oxygen or the less oxygen, this happens when the production is less than the consumption. So we can have a less oxygen. In this case, it takes oxygen from the atmosphere. So this exchange is keep on taking place in the ocean surface. Therefore, some region we call it as sink, or some region we call it as source. And the solubility of the gas, that is may not be the oxygen or any gas, that will be that is a function of temperature, salinity, and pressure. Higher the pressure, the gas solubility is more. So, for example, at a higher pressure, we can inject, like in case of soda, if you just imagine, higher the when we inject higher pressure, we can inject more CO2. But a lower pressure, we cannot inject that much CO2 like what we see in like a kind of salt. So in the same way, the ocean, from the surface to the deeper layer, the pressure increases, and therefore the solubility of the gas increases. Then second is the temperature. So higher the temperature, lower the solubility. That means the temperature is inversely proportional to the solubility. If the temperature is low, we can have more oxygen, or we can have more gases in the lower temperature. Similarly, in case of salinity, so the salinity, temperature, and pressure are the ones which governs in which the region it can absorb more gas from the atmosphere, or in which the region we can absorb less oxygen. less gases. So this is the one of the main reason you will have the same. We will not have the same proportion of gases in the atmosphere and the ocean. So if you look at the gases in the air and the gases in the gases dissolved in the seawater, that always will have equilibrium in the surface layers. So we know there's much of the in the air, nitrogen is contributing more. That means almost 78%, 79% of nitrogen to the total gas, 21% of oxygen, and 1% and very little about near 0.04% of carbon dioxide in the atmosphere. But if you see in the ocean at 15 degree or temperature or 35 degree, this is the value shown at 15 degrees centigrade and 35 salinity. There is a 59 or nearly 60% of nitrogen and almost something like 34% of oxygen and something like 2% of argon and nitrogen. Argon and carbon dioxide because of the difference in solubility. That means the water, the solubility of carbon dioxide is much more compared to the oxygen and nitrogen. That's why we have a very high carbon dioxide percentage compared to the atmosphere. So we cannot interpret that the atmospheric gases are directly dissolved in the oxygen, but it depends. Not in the same proportion, but depend on the temperature and salinity. And the biological production may not be in the ocean, but even on the land. All the plants, they do photosynthesis to get energy. So they use the solar energy using carbon dioxide and water. They will produce the carbohydrate. Then the oxygen will be released to the atmosphere. And this process we generally call photosynthesis. This process occurs mainly in the daytime. That means during the photic time. In the ocean, it occurs in the photic zones. That mainly up to 100 to 150 meters, the mostly. And at the same time, during the respiration, that will happen in the inner water column, or may not be in the photic, or that will be in the entire water column, the respiration process. That means the consumption of oxygen or the will happen in the entire water column. And one of the main things like not only in the daytime, nighttime also. The day and night, the respiration process will happen. And because of that, the column dominates the respiration process because it is happening in the daytime as well as in the nighttime. Now, the organic matter that will be produced in the surface layers, once they decay, it will sink to the deeper layers. During this process, much of the nutrients and the carbon dioxide, all these things will be released to the water column, and leading to removal of oxygen and accumulation of carbon dioxide and nutrients in the deeper layers. And therefore, if you look at the typical profiles of respired elements, or if you look at the typical profiles of oxygen, carbon dioxide, or the nutrients in the ocean, you can see in the surface layers, there's a high concentration of oxygen in the surface layer, and because the oxygen is mostly, there is an exchange of gases. First of all, there's a high, the oxygen is produced because during the photosynthesis process, and because of that, the concentration of oxygen is high in the surface layers, and when we go down, the deeper layers, the oxygen is getting consumed. That means the decay process is happening in the intermediate layers or in the different intermediate layers. So mostly this respiration or this decay process is happening in the intermediate layers, mainly between 100 to 1500 meters. Most of this organic matter what they produce in the surface layer get consumed or with respirate, and which consumes a lot of oxygen, and will have the oxygen minimum zone where the oxygen is minimum required, and below that there is the consumption is very low, and the oxygen profile or the oxygen concentration is in this debate. And there's another reason because of the convective belt, the different water mass, this oxygen is much higher in the bottom layers, and the consumption of oxygen is very low in these layers. And when the oxygen is consumed, or when the decay process is happening, the carbon dioxide, it also releases the carbon dioxide and the nutrients, nitrate and phosphorus, or the other silica or whatever it is. So in this oxygen minimum zone, the carbon dioxide or nutrients are getting respired, and the concentration is more in these layers. And if you look at the global primary production, the profile is satellite images. There are some regions where the productivity is very high. If you see, especially in the northern Indian Ocean and all, the productivity is very high. The color scale, you can see the red color is more productive, and the other zones are least productive. So other zones in the tropical Pacific and equatorial Pacific, mainly the equatorial regions, are highly productive. The reason is that in the Indian Ocean mainly, we have strong upwelling in the Somalia and Oman coast and the Indian coast. And the equatorial Pacific, we have the equatorial upwelling occurs throughout the year and brings more nutrients to the surface layers, and they have high production in this region. Obviously, because of the high production, the sinking of carbon is more, the sinking of organic matter is more, and because of that, the intermediate layer, we can expect more oxygen consumption, and they'll have the minimum oxygen in these waters. That means the high primary productivity, and because of this high export production is happening mainly in the tropical region and this upwelling region. We have this one of the main reason for the most intense oxygen minimum zone in this region. And there is another reason is the horizontal adduction of oxygenated water mass. You can see, especially in the Arabian Sea and the northern Indian Ocean, the northern region is landlocked, and there is no horizontal the adduction of water to the top, and the oxygenated waters are mostly transported from south to north. And some regions, mostly in the northern part of the northern Indian Ocean, is highly deoxygenated, or there is the oxygen, the intensity of oxygen minimum zone is more in this region. And also there's another factor that controls the salinity, is the stratification. When there's a more stratification, the lower the dissolution from the top, and because of that is one of the main reason we'll have the oxygen minimum zone. So this is the just see this. Just imagine this figures, and just see this high productive and high export of carbon zones will have more. This is the oxygen profiles at that 300-meter water depth, and you can see the most of the oxygen minimum zones are situated in this high chlorophyll or high protective high carbon export zones. This is about the mainly the open ocean oxygen minimum zones, and it is not only the open ocean. You can see the oxygen minimum zones, but we can see the oxygen minimum zones or the low oxygen zones in the coastal region as well. So the left figure, this is these dots are represents the region where you have the oxygen minimum zone. The yellow regions are mostly the eutrophied zones, and in the right hand side you can see after 1970, the oxygen, the hypoxic zones in the coastal regions are exponentially increased. So this is mainly the reason for more oxygen minimum zones in the coastal waters. There are two. One is the natural process through the upwelling that brings high nutrients waters from the surface to the from the subsurface to the surface layers, and the other reason is the human-induced eutrophication. That means the agricultural pollutants, sewage, etc. All this brings high nutrient load to the coastal region and can support high organic matter production and hence more oxygen consumption in the bottom layers. So these are the mainly two processes that governs the oxygen minimum zones, the oxygen deficient zones along the coastal regions. So if you look at the ecosystem dynamics of Eastern Arabian Sea, this is one of the very interesting region where we have upwelling in the summer monsoon, and this because of this upwelling we have high primary production mainly during the summer monsoon season from June to September mainly, and this is the season we will have the fish spawning as well as the high productivity will support the fish egg and larvae, and you have high fish production during this season. But at the same time, we'll have the upwelling, and this upwelling will bring hypoxic waters to the coastal region, and also it will bring the high carbon dioxide waters to the coastal regions. And I divide our region, the west coast of India or the Eastern Arabian Sea, into three regions, mainly the northern Eastern Arabian Sea, central Eastern Arabian Sea, and the southeastern Arabian Sea. So the southeastern Arabian Sea, where we have more the intense upwelling, and will have more productive region, and the central region also have a good amount of upwelling during the summer monsoon, and the northern region will have limit the upwelling intensity is not that much strong compared to the south and central. So you should imagine or you should keep in mind these things south we have high upwelling, south and central we have very intense upwelling in this region, and the north we have the intensity of upwelling is not that much high. And there is a thought or there is a thought that the increased the region of this Western Indian Shelf has very high nutrient load from the coast, and because of that there is an intensification of anoxia over this region because of the high nutrient input from land. And there are these papers mainly this paper published in Nature in 1990, and with a limited data set. And when we look at over the years, we found there is no intensification, but there is a kind of intra-annual variability. and because of that, there is a in some years there is a kind of high, there is intensification of anoxia, and in some region there is a there is no it never reached to the NOx. And for that, like recently we had a very massive observation along the coast, like 10 different. We have observed this region like a 10 different station, different transect we covered. Something like we had repeatedly went to the field. So we had a year-long observations in this region, 10 repeated observations we had from this region, and we found the anthropogenic nutrients. Like if you look at the right figures, the left, the figures in the left, you can see the dissolved organic nitrogen or dissolved organic carbon and the nutrients. The nutrient loadings in the central region, especially from the Central Arabian Sea, is much low compared to the north and south. So we thought like earlier there was like hypothesis, like it is not hypothesis. There was the people were thinking the intensification of anoxia is mainly because of this high nutrient loads. But we found the nutrient load is little compared to in the central region, in this region compared to the north and south. But we have high. This figure is like sorry, I didn't say this figure is the bottom oxygen deficiency along the coast during the summer monsoon, peak summer monsoon period. So we found the central region has high oxygen deficiency. That means the red color is high oxygen, the low oxygen condition. So this high oxygen condition, high oxygen deficiency or the low oxygen condition is very prominent in the central region where we have low nutrient load from the land compared to the north and south where we have the high oxygen content compared to the central region. So when we see the reason for that, this is the isotopic signature that also reveals the central region has very low nutrient load from land. So we found the central region has the biological, the oxygen, the biological consumption is also very low. The column chlorophyll production is very low in the central region compared to the south, because south has very high, very intense production, but it is still like the southern region has the hypoxic waters, but the central region where we always observe the anoxia has low column chlorophyll production, but high oxygen consumption in the bottom waters, especially the bottom waters, and where we have the anoxia. And we found like this is the oxygen, the development of seasonal anoxia over the Indian shelf. The figure shows the oxygen concentration, the bottom oxygen concentration in the around the western Indian shelf during May to December, May, June, August, and September. So June, August, September represent the early upwelling period, the peak upwelling period, as well as the late upwelling period. So if you see the bottom oxygen concentration, May we have enough of oxygen, and in June you can see in the central region the oxygen started declining. That means the low oxygen waters started coming over the shelf region, and the August and September we have seen very intense oxygen deficiency in these waters. So what we found is like the central shelf is more vulnerable to seasonal deoxygenation. This is mainly attributed to the upwelling intensity and the source water. You can see the June, the open ocean waters are like it is the 100-meter depth waters. They are more there is a intense oxygen deficiency in these waters. So these oxygen deficient waters are entering to the coastal region. So by time, these low oxygen waters, they are reaching to the shelf region, and the other regions, north and south, the open ocean has relatively high oxygen content in the upward waters. So we found the oxygen deficiency or the intensity of oxygen deficiency in the central region is mainly attributed to the source of oxygen content. And if you see the this is like the monthly oxygen. This is from the Kochi region, the shelf region, Kochi shelf, and you can see the monthly variation in oxygen profiles. Y-axis represent the depth, and the x-axis represent the distance from the coast. You can see January, the entire water column is highly oxygenated, and the February you can see from the bottom there's a low oxygen, the adduction of low oxygen waters. That means there's a initiation of upwelling from here itself. This the upwelling, the temperature profiles I didn't show. From the temperature profile also we can see the bottom waters in the shelf waters are already low in their temperature and low in the oxygen in the bottom layers. And these low oxygen waters slowly enter to the coastal regions, and they progressed in April, and by May the entire bottom waters are spread with the low oxygen waters. And by June and July, the bottom oxygen deficiency intensifies, and by the late September, late summer monsoon, the bottom waters become more oxygen deficient, and then after September, there's a withdrawal of upwelling and into oxygenated gains. So in the right hand part, you can see the from January to December how the oxygen concentration varies in near shore, inner shelf, and mid shelf and outer shelf of the Kochi region. You can see there's the oxygen deficient waters from something like January to from March to October in the shelf region, and the near shore region it is something like from May to September. You can see the oxygen deficient waters in the shelf region. And because of when we say the low oxygen waters, what it really means, we generally classify as oxic waters or something like a hypoxic, from something like a 0.2 to 2 milligram per liter. That means more than 63 micromole of oxygen. Or below that, generally we call anoxic. Mostly the biologists they use this particular definition, and by generally the chemically we generally call when there is a enough amount of oxygen, we cannot see the nitrate or the nitrite enrichment. So when there is a hypoxia, the hypoxia generally called as there is a zero nitrite NO2 concentration. When there is a NO2 or the significant amount of NO2 is there, we call it as suboxia. During that time, the hydrogen sulfide is not present, and when there is a presence of hydrogen sulfide, we generally call as anoxia. So during the hypoxia is mostly tolerated by some of the organisms, but during the suboxia and anoxia, when there is an intense oxygen deficient condition, many of the biological organisms cannot survive in this condition. So in our region also, we generally see in the central region where we have very high oxygen deficient condition, we will have a fish kill in the central region especially. And this is mainly because of this low oxygen waters like reaching almost to the surface layers. And this, as I said earlier, uh, during this period, the summer monsoon time, because of the high production due to upwelling, this region is highly like it supports a lot of fishery. And because of the because entire bottom layers are completely hypoxic or anoxic in nature, these fisheries resources, all these fishes get accumulated in the water column, in the very limited water column within the 10 meters or 20 meters in the surface layers. They get trapped in the base and get uh, uh, transported to the shore regions, and we have seen this fish kills during the late summer monsoon period when there is a intense anoxia over this western Indian shelf. And of course, there are some, if you look at the entire global ocean, there are some fisheries that can tolerate the hypoxic or anoxic situation. There are some fishes uh, that can survive in the low oxygen condition or the oxygen minimum zones. And also, because of the low oxygen condition in the shelf, you can see the benthic diversity also significantly declined uh, in the region, especially the region where we are seeing the significant oxygen deficiency. Central Indian region. So there's a significant decline in benthic organism also we see as well. So this difference in benthic organism, like the significant decline in macro and neofauna also we have seen, and this also have a very huge impact on the biogeochemical perspective that I will talk later. This is another thing, like it is not only the oxygen that exert pressure to the biological organism. It is the pH. During the upwelling period, we have very intense or very low pH condition. It will reach up to 7.5 or sometimes, and they will have very low, very high DAC concentration. That also exert very significant pressure, significant pressure on the biological organisms. And because of this high, very low and very intense DAC, the high PCO2 conditions, the calcium arenate saturation levels will also go up to like sometimes 1.2 or near 1. That is almost we call it as threshold for many of the calcifying organisms. So we have seen many of the echinoderms, like a pteropods and some of all these organisms that use the calciate or arenate uh, calciate or arenate minerals for their shell making. So the significant decline has been observed during this process because of the intense seasonal oxygen deficiency along the coast. And again, just because of this central intense oxygen deficiency, it is not only affecting the biological organism, but also there are this will influence the significant changes in the redox sensitive elements. So if you look at the during the oxic process, it is something like a very little amount of uh, they need to use very little energy during the oxic period, and when there is a low oxygen condition, the organisms need more energy to degrade the organic matter. So they will always, when there is low oxygen, when there is an oxygen deficiency, they always find some other oxygen species like nitrogen oxides or iron oxides or manganese oxides for their for the degradation of organic matter. So first they use the nitrogen oxides. So when there is a utilization of nitrogen oxides, it will produce nitrite accumulation, or then again, if they use the oxygen in the nitrate, it will there will be an accumulation of nitrous oxide and some amount of nitrogen also escape in the form of nitrogen. This process we generally call as denitrification. So when there is a this oxygenated species, this microorganism always prefer the nitrogen species because the relative amount of energy they need to break this bond of this nitrogen oxide is much low compared to the other species. So they prefer the nitrogen species first, then the iron and manganese oxygen species. Then they use the sulfate species, sulfur species, sulfate. Mainly during this process, we always see the escape of hydrogen sulfate, and after that only the organism will use the carbon dioxide species. During this process, it will produce, it will oxidize the carbon dioxide to the methane. And there is also some other process happening parallelly called anamorphs, or kind of DNR process. Different processes are happening simultaneously. In Arabian Sea, denitrification is one of the most dominant process happening. That is one of the most important nitrogen loss process, as well as the nitrous oxide accumulation of nitrous oxide happening during this time. And because of that, Arabian Sea is also considered as very high source of nitrous oxide during the summer monsoon period because of the low oxygen condition happening in this region. And if you look at the nitrogen or the nitrous oxide buildup during the, especially during the Noxic period or the low oxygen period in the south and central regions of Arabian Sea. South, we have the oxygen content is relatively high. You can see the bottom layers have at least 20 micromole of oxygen. That means it is still in the hypoxic condition. But in the central region, we have the bottom waters, oxygen is completely utilized and it is almost anoxic. And we also measured the hydrogen sulfate in this bottom waters of central region. And you can see very high amount of nitrous oxide accumulation happening over the central region. This is from the, this is a section in the central shelf, and this is from the southern shelf. So this compare the central southern region as well as the central region of the Indian shelf. So you can see very high amount of nitrite accumulation. So the red region shows high accumulation of nitrite or nitrous oxide in the central region, and the blue indicates in the southern region. You can see there's a very huge amount of nitrous oxide or the nitrite in the central region. In the red color you can see, and then there is a very low oxygen, especially below 20 micromole. You can see exponential production of nitrite as well as nitrous oxide. It is mainly indicates the indicate the denitrification process happening over the this region during the low oxygen condition. Also, you can see other greenhouse gases, CO2, the accumulation of carbon dioxide and nitrous oxide. If you see, when there is a very low oxygen condition in the carbon dioxide or nitrous oxide, it is something like a accumulate, or there's a very huge amount of this gas production during this low oxygen period. And this is the budget we have calculated from the Western Shelf. You can see the Mangalore region, and that means the from the central region, you can see very high amount of greenhouse gas flux from the central region during the summer monsoon, especially, or the annual budget of the nitrous oxide. This is the nitrous oxide flux for the year 2012, and you can see very high flux of nitrous oxide because of the very low oxygen conditions. You can see the bar plot as well. There's a high flux of or there is a high nitrous oxide and a methane flux, and nitrous oxide and carbon dioxide flux during the, especially during the peak upwelling period. At the same time, you can see there is a reduction in methane during this. See, there is a methane is just opposite to the nitrous oxide and carbon dioxide. So we are very much surprised to see very low methane concentration during the low oxygen condition. So if you see the seasonality in methane cycling from April to December in the Cochin shelf, you can see very high oxygen, very high methane concentration, especially in the nearshore region. This is the distance from the coast in the x-axis and depth in the y-axis. You can see the nearshore region very high methane concentration, and then low oxygen water centers during the June, July, and August, the September period. You can see it is something like 100 plus during the April period, getting reduced to something like a 30 or below 30 nanomole concentration of methane during the monsoon period, and after the withdrawal of upwelling or the we can see an increase in methane concentration again in the coastal waters. It again increased to 100 or 100 plus. Okay. So when we plot this down below, you can see the bar plot indicates like the methane concentration in the nearshore region. You can see a significant reduction in methane concentration, especially from June to September. During this period, just think we have observed very high nitrous oxide and carbon dioxide production, but we are seeing very low methane concentration compared to the other season, compared to the other months. So we have in the nearshore region, we have mainly two source of methane from the estuaries. That is one of the major source, and we expect a methane source from the upwelling. But during the upwelling period, we are seeing the low methane concentration in the bottom waters as well. But when you see the pattern in the estuaries, we have observed, though there is a significantly or the comparatively high methane concentration in the estuaries, lower and middle and upper estuaries, that is during the September, we are observing low methane observation in the nearshore regions. So it is just opposite. So that means there are kind of dilution happening, dilution or oxidation that we need to check happening during the monsoon period in the coastal region when there's a hypoxia enters in this region. So we observe similar behavior in the central shelf also. You can see central shelf is much lower compared to the southern shelf. This is from the southern region, southern Eastern Arabian Sea. This is from the central Eastern Arabian Sea. So we have two options because we have already seen from the estuaries there is a significant amount of methane is coming to the nearshore region. So we thought of we have observed the bottom waters having very high methane concentration, and we thought there is one of the main possibilities. There's a decrease in sedimentary methane flux, or there's an oxidation is happening over the hypoxic period. So what will be the reason for the less sedimentary methane flux? When we look at the sedimentary methane flux, the methane we found there's a absence of or there is a less sedimentary flux because of the active bioturbation. So if you look at this figure, the
Sorry,
sediment.
Suji, let me interrupt you. Sorry. Can you conclude for the next 5 minutes?
Oh,
I want,
I didn't
yeah?
check. Yeah, it is in
It's
control.
really interesting, but
Yeah.
I'm afraid people have
So
to
if you look
go
at
back to
this
their
figure,
car.
so with this figure I will conclude. So if you look at this figure, during the Oxic period, it has seen all these bioorganisms, the benthic organisms very active in this region. So when there is an anoxic waters, all these microorganisms, that is one of the main bioturbator in this region. They are the main. They are mainly completely churning the sediment over this region. So when there is a all these bioorganisms or the higher microorganisms are active, the methane what the produce in the sedimentary layer will escape very easily to the water column and will have a high methane production in the water column. So when there is a the absence of the bioorganism, the macrofauna in this during the because of the low oxygen condition, the methane getting released because of the bioturbation is very low, and during this process, because it is very slowly, it is releasing from the sediment to the water column, and much of the methane is getting oxidized because of the chemical reactions happening, methane dependent oxidations happening over this region. Methane dependent or the iron manganese dependent oxidation, dependent chemical reaction is happening. Very little methane is being transported to the water column, and because of that, the methane concentration we found low during the anoxic period. And there are some other interesting process like dependent process also happening during this process. Because of that, we are end up with very low methane concentration during this process. So this this is one of the interesting result we published in Frontiers in Marine Science recently. And with this, I will conclude. Okay, thank you, Lika.
Thank you. Thank you. Very good. And super interesting. I have questions myself, but maybe I should ask the audience first. Could you raise your hand or type your question in the chat and we can read to Sudheesh? Onur?
So,
hello. Great talk, Sudheesh.
Yeah,
that's a long time. It's really good talk. Yeah, thanks a lot.
Thank you.
I mean, I learned a lot about Arabian Sea. It's really good. I mean, you're always a very good presenter anyway. And I have one question. Like, it's very interesting. All you showed about oxygen, methane, and fish kills, and I was really impressed of your findings there. But do you do any modeling, like in your university, about these phenomena there?
That is one of the main drawback. Like we didn't do any modeling, but we have a lot of data set we collected. Like I show here, we have kind of like 10 repeated observations we completed, 10 transect along the coast within a year. So we have collected all this data, like we are being analyzing now. And we hope like after the preliminary analysis is still going on, some of the papers is already published. And after that, the data will be transferred to the data center. And there we have a very good modeling team. I think they will take up the data.
Okay.
But still, like the biogeochemical modeling, the modelers what we have in our team is like we don't have actually.
Okay. Yeah. Great. I'm looking forward to see. Like what,
yeah, because now you are doing most of the like a kind of opposition.
Yeah.
Because
maybe we can do together. I mean, that's also possible, right?
Yeah, that we can think of. Like one of the main thing is like this coastal region, or this region is like a very dynamic, very dynamic. So because of that, like most of the modelers, because coastal regions very few are looking at the coastal regions. Most of the modelers are mostly looking at the open ocean region because it's not that much complicated compared to the coastal region.
Yeah. Yeah, thanks. Great.
Thank you. And we have a comment in the chat from Luis Escudero. Excellent presentation, Sudheesh. Congratulations. In Peru, we developed an algorithm to estimate the OZM using information from the acoustic echo sounder, and it works very well, especially for our anchovy biomass evaluation studies. Regards.
Yeah, that is great. Actually, we also have some some of our team. They're also in the acoustic data sets because that is, but I am not that much into that. So our fishery teams mainly that we have the fishery research, fishery oceanography research vessel. So we have a facility, and now in the future 2047 plan. Now the 25 years plan is like underway. So they are looking at those aspects. So that will be very interesting.
Before I give the word to SOA, I have a curiosity. Have you approach local fishermen in Goa, traditional fishermen, and ask them about these fish kills, if it's something that their parents and grandparents mention, it's something regular?
So in our region also, in my region also, people sometimes the northern Kerala also have seen this fish kills sometimes. So they have their own kind of stories. So sometimes there will be some smell from the sea. So they have their own terms. But they are really don't know what is happening.
It would be interesting to merge their knowledge with this data you're creating. Sometimes, you know, if it's increasing or not, even if it's not anthropogenic, it definitely there will be an influence there. And they probably observing this much longer than we are. Okay, SOA, please.
Yeah. Yeah. Great talk. I'm very happy because this is really great talk. I learned a lot, and thank you for this presentation. And basically, it's just one question that I have is because you highlight about the central region, because it's there that you during the strengthened by the expansion from the offshore to the coastal zones. Yes, I was wondering, because you highlight that there is two process that can control the oxygen level in this coastal zone, which are basically due to the higher upwelling process during the summer season, or maybe due to the eutrophication, which are that I guess might be the impact of the land to the coastal zones. But you didn't probably highlight the contribution of the eutrophication, probably, I mean, the nutrient that are loaded to the system during the summer season. What are their contribution to the development of the apaxia zones? And I was wondering how much is the contribution of the river. And for that, I want to join the owner regarding the modeling aspect. Maybe you get into the model, then probably you can get into account the main process that can control all this. And I guess maybe it's the advection that is playing the main role for bringing this water from the offshore to the coastal zone. But now, what about the contribution of the river imports? I'm not sure if I'm clear, but this was my question. Yeah, thank you.
Yeah, that is a very interesting aspect, because the contribution of each process, it is very much important. As you suggest, modeling can only answer that question. And when you see, if you see this particular figure, you can see the central region has very high oxygen deficiency, but the region has, this is the right side, the bar plot indicate the nutrient loads from the nearby estuaries. So we had measured the nutrient load in the nearby estuaries, and you can see the central region has little nutrients compared to the north and south, where we have like the central region has, but we have the, though we have a low nutrient load, we have high oxygen deficiency. That means the from the it is not from the nutrient load from the land. That is one of the main thing. But if you see the source waters, the oxygen concentration, the open ocean in the open ocean oxygen minimum zone, you see the bottom it is like the offshore waters is from the 100 meter, and the bottom water and the shelf waters we consider like the bottom waters. You can see the open ocean waters during June, they are much like the more decrease in oxygen. The content of this upfilled waters in the central region are low in the oxygen content, and these low oxygen waters are reaching to the coast. And some of the biological process, as I said, happening over the shelf also contribute the intensification. But the main reason we found is the source of these upward waters. So these regions are the central regions are mostly attached to the connected to the core oxygen minimum zone of northern Indian Ocean, and this region have very intense upwelling. So these core OMZ waters from the offshore region are transported to the central shelf because of the intense upwelling. But southern region, we have the freshening from the south, and the oxygen concentration in the south, like the oxygen concentration in the OMZ of south is more compared to the central region. In the northern part, of course, there is a intensity of upwelling. The upwelling is not that much prominent. And if there is time, I can show you some of the other figures, but I don't know whether he is convinced with my answer. I'm not sure. But the contribution.
No, it's okay. Yes, yes.
And the
no, it's okay.
Okay. Yeah, and of course you can. I don't know if SOA has Sudheesh's contact, but I can easily put you two in contact to continue discussions.
Yes, I would be very happy. Yeah, thank you.
Yeah.
Rita.
Thank
I
you.
would be very happy.
Shaheen, please.
Hey Sudheesh, nice presentation. Congratulations. Thanks for presenting the work, Mida's work part and everything, all your work. I was just wondering, like, when you say it's more of the seasonal impact on the low oxygen conditions, do you want to say that we should not worry about the anthropogenic input in that case?
That is a great question, because definitely we should worry about, because as you see, like now we are not observing that much anthropogenic flow to the coastal region, but still we have very high oxygen deficient condition in the coastal region. So just imagine if there is a anthropogenic impact of anthropogenic influence too. So if we have more nutrient load from the land, the intensification will be much more, and the condition is much worse, and we'll have more fish kill or more impact on the biological organisms as well. So definitely we should worry in future, but we should closely watch the region for not to increase in like any anthropogenic load, or to study or learn more about the biogeochemistry of this region, or the biological response of this region, because there are two things. The biological response can be because of the low oxygen condition, or because of the high PCO2 or low pH conditions. So these two factors, like the deoxygenation as well as the acidification, because of the upwelling happening over this region. So we should be much more worry about in future, worry in future, because not only because of the anthropogenic load we are expecting, but also for the increased carbon dioxide in the atmosphere, or the because of the acidification condition happening over the world ocean.
Thank you.
That's right. It's your partial pressure of CO2 values indicate that during the monsoon it's releasing. It's a source, and of the monsoon it's a sink for carbon dioxide. Yeah.
Yeah.
Okay. Cool. All right. I'm afraid we are short in time already, so I would like to thank everybody for their presence and participation here, and special to you, Sudheesh, for kindly accept our invitation and give such a great presentation. We will include the recording on YouTube later on, and we welcome everybody again next week. We're gonna have another presentation, interesting. So on Monday we will start circulating the poster for the next webinar. All right, thank you very much, and have a lovely weekend, everybody.
Yeah, thank you.
Thank you, Suji. Bye bye, everybody.